Hello, F-sharp. I wanted to take some time to unpack an article that I recently wrote titled, "What is Going On with Software?" And this article was prompted by my mulling of the state of the software industry, where we're at and where we are going. And part of it is I've been asked to give a talk of why F-sharp is a great language for doing high performance work, simulations, optimization. And so in order to set that up, I decided, hey, I'm going to write a series of articles which unpacks my thinking around this domain. And then I can distill that down into a set of slides that I'm going to give for a presentation. Now, in this article, I kind of explore where are we at in the software industry. And the main thing that I am struggling with is the performance of our applications. Now, I am not a computer scientist by training. I'm a chemical engineer and an industrial engineer. I just happened to write enough code that I kind of got anointed at some point and saying, okay, you are now a developer. Okay, which has been great, but it means I have a different perspective on the situation than someone who has been in computer science for a very long time. And in this article, where I start out with is kind of exploring, hey, what are the common paradigms that we are using for composing software? Now, object-oriented programming is the dominant paradigm still. Functional programming has made a lot of headroads. And what we are seeing is that a lot of classically object-oriented programming languages have added many functional features. And that's great. But functional programming still isn't going to save you at the end of the day. I do believe using functional style of composition will end up creating more robust, testable software. But there is a challenge there because naive functional programming will lead to terrible performance with your CPU. And this is one of the things that I was starting to express here in the first couple of paragraphs is that when I first programmed, I wrote some quick basic back in the day. I specifically had a friend who had a computer with the game Star Control on it. And I really wanted to be able to play Star Control on my PC, but I didn't have enough money to go and buy the game. So like, okay, well, I know that QBasic exists on my system, so I'm going to program a little silly game and make my own little Star Control. That never ended up panning out. I did have triangles flying around, but that was it. But the PC that I was working on was a 386. And the 386 was a 40 megahertz single core CPU. And what I'm currently working on several decades later is an Intel 13900K. It has 8 performance cores and they can sustain 5.4 gigahertz or 5,400,000,000 CPU cycles per second. And if you do the math, that is over 1,000x improvement in speed. But when it comes to our experience of software in the day-to-day, applications don't feel like they are 1,000 times faster. Now, granted, the amount of data that we're processing, the amount of things that we are doing, and the sophistication of what we're building is higher. But I don't think it's 1,000 times higher, which means we should be realizing performance gains. We should have faster applications. We should have a faster experience when we work with our PCs. But on the whole, I don't think we do. Yes, there are some applications that are legitimately faster, but software just seems to be much slower than it should be. And that really bothers me. And when I look at my own code, I see that I now write code that is far faster than the naive code I wrote at the beginning of my career. And part of the reason I believe that is the case is in this next section is abstraction. Now, abstraction is an incredibly powerful thing. It allows us to take very complex things, decompose them into smaller, less complicated domains, and create an abstraction around it. And that is wonderful because to be able to build a large system, it is much easier to make small systems and then to compose them together. Now, object-oriented programming and functional programming have different approaches to how you do that composition. But there is a downside to abstraction. It causes you to lose sight of how complicated your software actually is for the CPU. You lose an understanding of just how much work you're asking the CPU to do. Now, this was the right call for the software industry. I'm not questioning that. We needed more abstraction. I mean, back in the day, we had to write in the machine code of the computer that our software was going to run on. And then, thankfully, we got things like C, which kind of abstracted the particular hardware we were running on. And so we were able to target multiple CPUs with the same code base. So that's a very useful and powerful abstraction. But we have added many layers of abstraction on top of that. One example is garbage collectors. And so like, hey, we don't want to have programmers dealing with the minutia of managing memory. So we will create systems for automatically doing that for them. And again, this made sense at the time. I'm not questioning that. Programmers were very expensive. The need for software was tremendous. Like there was so much need for new software to be developed that we needed to maximize the utilization of developers. And so if we could take things off the developer's plate so they didn't have to worry about them, they could then focus on the particulars of the problem they're trying to solve without getting bogged down with the minutia of memory management, for example. Now, again, what that does, though, is you start to lose sight of how much work you're asking of the CPU and how difficult of a problem you're giving the CPU. And it's gotten to the point where, and again, I mentioned in this paragraph, that it is very common for me to talk with a developer who has no concept of caches inside of a CPU, registers, L1, L2, L3 cache, main memory, how those things interact, things like branch misprediction. And I don't blame them either, because most of the industry says like, hey, you don't need to worry about that. CPUs are fast. Compilers are pretty fantastic. It'll just make it faster for you. So again, we're adding these, there's so many layers of abstraction now that a developer can lead a very successful career with having no understanding of how a physical CPU actually works. And in this paragraph, I kind of point out, I find that rather odd. And the reason I find it odd is because in other engineering disciplines, you're never allowed to ignore the physical realities of the problem that you're trying to solve. For example, a civil engineer who's been asked to build a bridge, design a bridge, they have to take the physical realities of where that bridge will be built into account. They would never have the abstract idea of a bridge and say like, hey, we're going to inherit from this and implement it. Like, no, they would be keenly aware of where that bridge needs to be built and take those restrictions into account. So they would want to take that problem-specific data and integrate that into their solution. Same thing with industrial engineers. An industrial engineer is someone who classically like lays out a facility and puts workstations in different areas and designs that workstation so that human beings can be very efficient as they operate inside of there. And an industrial engineer needs to take the physical layout of the building into account. And chemical engineers, when they design a chemical manufacturing process, they have to be aware of the ambient environment so that their chemistry can run successfully. And it's in the software industry where I find it bizarre that we're encouraged to ignore the physical realities of where our software needs to run. It is so counter to how what I believe every other engineering discipline behaves. It's a very strange divorce that's going on. Now, some of you may be saying, hey, Matthew, you're talking about taking problem-specific stuff into account. This is and designing with that particular thing into account, but like now we're losing the power of abstraction if we're building for a very particular set of data or a very particular domain. And it kind of sounds like this idea of like premature optimization, perhaps. And that quote, premature optimization is the root of all evil, is a really interesting one. And I want to bring up that paper. So that paper, that quote is coming from the paper, Structured Programming with Go-To Statements by Donald Knuth. And the quote itself, and this is a fantastic paper. You should go and read this paper. It's very good and very insightful even today. It's incredibly relevant. But this quote is actually on page 8 of it. And I'm going to go down to it so we can see it in context. And it's right here. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. And so what Donald Knuth is saying here is that, like, hey, when we're obsessively chasing down performance, that's going to cause us to write really difficult programs to debug. But if we back up in this paper a little bit and understand like what the line is for Donald Knuth when it comes to performance optimization, we'll go over to here. Say the conventional wisdom shared by many of today's software engineers calls for ignoring efficiency in the small. But I believe this is simply an overreaction to the abuses they see being practiced by penny-wise and pound-foolish programmers. And if that doesn't make sense to you, this is kind of a British phrase where they have pennies and pounds. And so the idea is that someone is keeping very close track of pennies, but they're being very wasteful of pounds, which is a larger denomination of money. So it's the idea of like you're obsessive over these small details and you're ignoring the much larger issue that is at hand. But then he says, in established engineering disciplines, a 12% improvement easily obtained is never considered marginal. And so Donald Knuth is saying, hey, if you can improve performance by 12%, by doing some simple refactoring, that is absolutely worth it. Of course, we wouldn't bother making such optimizations on a one-shot job, but when it's a question of preparing quality programs, I don't want to restrict myself to tools that deny me such efficiencies. And there is no doubt that the grail of efficiency leads to abuse. Programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have strong negative impact when debugging and maintenance are considered. And so, for me, this really highlights how critical it is to have benchmarks and profiling guiding you when you're doing any kind of performance work. The quote, we should forget about small efficiencies, premature optimization is the root of all evil, yet we should not pass up our opportunities in the critical 3%. A good programmer will not be lulled into complacency by such reasoning. He'll be wise to look carefully at the critical code, but only after that code has been identified. It is often a mistake to make an a priori judgments about the parts of the program that are really critical, since the universal experience of programmers who have been using measurement tools have that their intuitive guesses fail. After working with such tools for 7 years, I've become convinced that all compilers written from now on should be designed to provide all programmers with feedback, indicating what parts of their programs are costing the most. Indeed, this feedback should be supplied automatically unless it has been specifically turned off. And I love this idea, and I want this so badly for my own code to show me how complicated my code is for the CPU. And now I want to show you an example of why all this abstraction is leading to very slow code, and why I think this idea of having this feedback from the compiler would be incredibly valuable. Now, here is a very simple example. Here I've created an fsharp record, and this is the tool that I'm using right now is the website, sharplab.io. And what's fantastic about it is you can put in various .NET languages and you can get various types of feedback. And what I am doing here is I am defining an fsharp record. This is a reference type. It's allocated on the heap. And then I have a very simple function where I'm taking in 2 instances of a chicken and I'm saying, are these equal? Now, this is a very convenient abstraction. Fsharp has fantastic defaults when it comes to equality. Fsharp types have structural equality. And so if the contents of 2 instances of the same type have the same values, Fsharp is going to say that is equal. And it is very easy to call that. You just use this equal symbols here. It's like, hey, is A equal to B? Now, the problem with this is that this very simple piece of code is hiding an enormous amount of complexity. Now, I'm not saying that the Fsharp language was designed poorly. That's not at all what I'm saying. But I'm saying this is an instance of where abstraction is now starting to cause us problems, because what you see here on the right, chicken test, this is the x86 assembly that gets generated for this equality check. And this is an enormous amount of code for it to run. And so if you have an algorithm and you're frequently checking the equality of Fsharp records, your code is going to be slow because this incredibly simple line of code ends up generating a huge amount of work. And so what I often like to do in performance critical code, and if I know from the outset that my code needs to run fast, if it's not just a one-off script, I would not compose my domain this way. I would end up using measures. And I'm going to define a measure here called turkey, type turkey. And now what I can do is I'm going to have turkey test. And I am going to represent turkeys by just using an integer with a unit of int on it. And so I'm going to say int turkey. B is an int with a unit of turkey on it. And now I'm going to say, hey, is A equal to B? And I'm wanting to know is A equivalent to B? And it's complaining about something here. Oh, I'm missing that closing angle bracket. And now when I scroll down to turkey test and I'm checking are 2 things equal to each other, it is 4 instructions, one of them being a return and one of them clearing a register. This is outrageously fast. This is orders of magnitude faster than that chicken test. Now, I know that, like, okay, Matthew, you've just used the unit of measure of turkey, you've annotated this int, but chicken here had name and size on it. Well, what I would often do is I would end up using a struct of arrays type of layout. And so I would say, hey, I'm going to have type turkeys. And what I would end up doing to represent this is I would have a name, which would be a string array, and I would have a size, which is a float array. And I would use this integer representing that distinct turkey to index into this data. And this would be incredibly fast. Now, I'm not saying this is what you should do all the time. Your algorithms and your memory access patterns will determine if one of these is faster than the other. But for me, things like this, these types of abstractions are an example of how modern languages have moved us so far away from the realities of what is happening on the machine that it's just invisible to us what pieces of code are actually very demanding for the CPU or not. And so I would love that feature that Donald Knuth mentioned, and be like, hey, I would love to get feedback from the compiler, which tells me, I would love it if JetBrains Writer or VS Code or Visual Studio could provide some feedback on top of here saying like, hey, when I assemble this, this is how many x86 instructions are going to be required to do this. And this is how many loads from memory, because that's going to be very quick feedback to me saying like, hey, you think this is a very small piece of code, but in the reality, it is mapping down to something far more complex for the CPU. Okay. Now, I think, and this is an example of, I think we're starting to suffer from what I'm calling abstraction hangover or abstraction addiction. We have so abstracted ourselves away from the problem of running our code. That's the problem we've abstracted away from ourselves. We still very much focus on the problem of the business domain and solving the business's problem. That's fantastic. But this other problem that was critical for our work, we have almost completely obfuscated from ourselves. We have no visibility of what we're actually demanding of the CPU. And it's because of stuff like that that I have found it relatively straightforward when I've been asked to go in and improve the performance of F# code by 10 or 100 times. And it's because of all these hidden things that you're just not aware of as being expensive because they've been so abstracted away from you. Now, what I also concede in here, and I want to point out, is the takeaway is not, oh my goodness, we just need to go back to C. Life was better. No, it was not. Life was not better. The solution is not, go back to the old ways or something like that, because a tremendous amount of good has come from these abstractions. And one of the examples I give is Excel and VBA. Many people's lives have been made far better due to Excel having VBA as a scripting language behind the scenes that they can automate components of their work, making their lives dramatically better. And we love to rag on Excel and VBA at times as developers, but we cannot deny the tremendous good that has come from it. So in this case, abstraction has yielded a lot of good as well. So what I'm seeing is that abstraction is a two-edged sword. It is not, we are very quick to apply it. There's the joke in computer science that every problem in computer science can be solved with an additional layer of abstraction. And what I think that we are seeing now is that that attitude, there's no opposing force to that attitude. The one example I think would be the games industry where performance is critical. And so performance is what pushes back on that. But in a lot of the software development industry, there is no opposing force to abstraction. And so we just keep layering abstraction on top of abstraction. In our cases, we take dependencies on other libraries. And again, we're abstracting the problem away from ourselves by making it somebody else's problem, and therefore even further removing ourselves from the work that we're imposing on the CPU. And this has led to some pretty gnarly problems in recent memory. And one example here is an article that I cite where a school could not turn off the lights because the lights were smart lights and the software for turning it off had a bug, but they couldn't get like the source code to fix it. It's something completely outrageous, right? We're just like, okay, that is an example of like all these layers building up has led to systems that cannot be maintained or fixed. Another example that has happened in recent memory is the left pad incident in the JavaScript ecosystem. And so many libraries were broken. And left pad, like that function is incredibly small. And the Primogen actually did a great video where he unpacked the left pad function that's in that library. But taking a dependency on someone else's library is another example of us abstracting problems away from ourselves, like further removing us from the CPU and the realities of how our software needs to run. And so down here, I start kind of unpacking my own personal reflection because I am a huge beneficiary of these abstractions. I tried to learn C back in the day, and I basically bounced off my head. And I don't know if that has to do with the dyslexia and just getting confused with the symbols and losing my place. C++ was incredibly painful for me when I tried doing some GPU programming with it. And so F# was a language that actually made sense to my head, but part of the reason it made sense in my head is because it abstracted so many things away. And now that I have more experience, I'm now asking myself, like, am I overly reliant on abstractions? Do I use them too much? Am I too quick to try to make things generic and abstract? Because at the end of the day, there's a real cost to that. And I think we are undervaluing the cost of abstraction. We see all the benefits of abstraction, but we don't consider, hey, there are downsides to abstraction, and it can be very painful. And two of the people that I cite in here, and they can rub some people the wrong way, but Jonathan Blow and Casey Muratori are two people that I am inspired by. I do not agree with all their thoughts and statements, but I have found much inspiration from them, and has caused me to be introspective about how I write software and ask myself, do I really need all of these abstractions? And so at the end of the day, I think that we need as an industry to take a step back and ask ourselves, are we building on the right foundations? Is having all this abstraction really good for us, or do we need to bring more of the realities of our compute environment back into play? And this is one of the reasons I've been excited for a lot of the performance work in the .NET ecosystem, is because we now have more access to how memory is laid out and how it is managed. And I think that we are going to continue to need more of that to push the performance of our programming, because just abstracting all of memory behind garbage collectors, like, there's real downsides to that. And we've been riding on the coattails of hardware performance improvements up till now. But that means that at the end of the day, we're not necessarily realizing the performance gains in our software that our amazing improvements in hardware should have brought us. So this is kind of where I'm at, and this is what I am wrestling with. And fortunately, I think F# provides a lot of the facilities to write very high performance code using a procedural style. And what I like to do is I like the core engine parts of my code are often written in a very procedural style. I have a joke where F# is my favorite language to write C in, because the structure of it is very C-like. But the external API that the user ends up using when they take a dependency on one of my libraries is they are going to have a functional API. It's going to be immutable. It doesn't use mutation. It doesn't expose mutation to the user. And I think that that is going to be a real sweet spot for software going forward, is like, hey, we want to have functional APIs, but procedural engine code for performance. And that's really what I've been exploring. So what are your thoughts on this? Is abstraction just universally good? Am I overblowing it? I would really appreciate hearing your feedbacks on what you think the challenges are with the software industry and where we're at and where we're wanting to go. So thank you very much for spending some time with me. I really appreciate it. And you have a wonderful day. Bye-bye.